This conference will now be recorded.
Okay, good morning, everyone. We are expecting Ravi Mahajan from Intel to discuss the IEEE HIR naming conventions or taxonomy. Also, MEPTEC had a pretty well attended, from what I can see, Road to Chiplets seminar series. I think they should be on online. So check out the sequence if you have some time.
Hi, Bobby. This is Peter.
Hey, Peter.
Did you get my email that I need to defer my presentation for next week to sometime
Yes,
later?
I did. I did. Sorry.
I didn't get the, yeah.
Yeah. So why don't I share my
Yeah,
screen?
so sorry that I could not get the permission this time. Sorry for that, making sudden changes.
Yeah, so I'm in fact, what I'd like to do is
So
yeah, it's unfortunate.
yeah.
Go ahead.
No. Once I have the permission, I'll let you know. I'm ready for a presentation, but not at this time. Sorry for that.
Okay. Anu, would you mind, Bill, if I don't have Ravi's phone number, if you do, would you mind checking with him? Bill Chan?
Okay, I'll send him a text.
Thank you.
Yeah, I don't have his number.
So one of the things I just sent out an email. So
Okay. Bapi, Ravi just sent me a note saying he's online waiting for permission to enter.
What the heck?
I'm online waiting to be admitted.
You know what? Hang on. I think I know what. Would you mind just sending him this GoToMeeting and say use this link instead? I think I know what happened.
Okay, sure. Let me do that now.
Thank you. Okay, so I'm going to try. I'm going to try and do a Bo test chip. DJ came up with a very clever name, calling an ODSA sprint. And the idea is that we will try and do sort of a figure out what we know and what we don't know, and at least get everybody on one. We'll produce some kind of an alignment session. So I'm trying to do that a 2-hour session for next week instead of Peter's scheduled talk. If the group, it's short notice, so I'm hoping the group will agree, but if not, we'll see. We have a few open slots after that, so if you have anybody who you think is interested, let me know. We are planning a POC workshop on 8/27 roughly. The last week of the POC is up and running. I don't know whether JP is online.
So, Bapi, on the ODSA Dev Sprint, we should define the goal. Yeah, we should define the goals very clearly to communicate to everyone what is it that we want to accomplish via this sprint, so that people are very hyper focused on 2 hours. At the end of 2 hours, we need to have at least some line of sight, if not direct arrival to those goals. So my suggestion is maybe you can use today's call as an opportunity to socialize or even fine tune those goals, so that people start thinking about the dev sprint when for the next call.
Yeah. If we, I think that's a good good thought. After once we have some time after Ravi's talk. Let me see. Right. Okay. So then the second thing I wanted to share is that the link layer group is going to go ahead and start developing the outline of a spec. or developing a spec. We have Arthur from Cadence has put an outline together. So if you have someone from your organization who's interested in contributing or participating, we're going to put this up on a Git repo soon and start filling in the sections. So we could use all the help we can get, but this is a fairly big milestone for us. So if you're interested, please join us in developing this link layer. Awesome, Ravi. Thank you. I'm glad you're
Sure.
here.
Can you hear me okay?
Yep, we can hear you. I can hear you just fine.
Okay.
Let me give you permission to present. Thank you, sir. Thank you again for.
Sure.
I have a hunch. I think you probably were on the Google Meet link as my guess.
Yeah.
Okay.
I was wondering what was happening.
Okay, it's all yours. Thank you.
Okay. Let me try and share. For some reason, it won't.
Do you want to send me your deck?
Sure. Actually, I am almost there, Bapi. I'll send you my deck as well.
No,
Yeah.
that's fine. If it shows you as logging on the web, and this has always had like issues with they're presenting through the web interface.
Can you see this now?
No.
It says sharing window.
Now yes.
Okay. Okay. Should I start?
Yes, please.
Okay.
So we go until 9. Take all the time you need.
Okay. So let me offer context, and I think this started with a discussion on nomenclature, but since I'm here and nomenclature is part of the overall heterogeneous interconnect, I figured we could look at the entire thing if that's okay with everyone. The idea, of course, is I don't know why this is okay. So we have a chapter 22 in the HIR roadmap, and the idea behind this chapter is to highlight interconnect characteristics and nomenclature or classification for 2D and 3D. And you will notice that I haven't done any 2.5D, 2.1D or anything like that, but describe 2D and 3D architectures in this. This is a broad industry and academia supported volunteer group that is developing this chapter, and the chapter is in a fairly good state of readiness. It's available online. And if you look at the list of people, I chair this, Subbu Iyer from UCLA co-chairs it, and Raja Swaminathan, who used to be at Intel when he started in this effort and then went to AMD and is now as AMD representing AMD in this chapter, is one of the other co-chairs, if you will. We also have a broad swath of technologists from OSATs, people who work on high-speed I/O and industry tech forums as part of this, along with academics. Okay. So this chapter, if you read it, has got 4 broad objectives. It says only 3, but let me point out the 4th objective. The first is we wanted to proliferate a standardized nomenclature that was essentially free of marketing, which clearly demarcated 2D and 3D constructions. It clearly said here's a way by which you can classify constructions. This nomenclature is by no means complete. It is something we have put out, and so far nobody has come back with an argument saying that it is incomplete. And we would love to get feedback and make sure it covers current and future architectures. And once we do this, then we look to define key metrics that say here is how the physical interconnects must evolve. Let me offer the rationale for why physical interconnects. As packaging engineers, our job is to make sure that we offer interconnectivity that performs, like it delivers the right level of physical characteristics so that power targets are met, that frequency targets are met, that we can deliver power, we can transmit information between entities on a package and off package. And what we have done is we have looked at all these characteristics and described them, and then we have described the characteristics of the power delivery and signaling that are needed to be successful. We divided this chapter into 4 areas. The first important area is the nomenclature, which I will talk to. Then we looked at attributes. What specific attributes should we offer designers so that they are able to design it? And then what electrical characteristics should we target so that signaling and power delivery can be managed? We also talked to difficult challenges, and it turns out that we started by we started by taking a very broad overview of the difficult challenges, but with the second generation of this chapter, we have come to some very specific targets. And one area that is not covered in the 2020 chapter, but will be covered in the 2021 chapter, is process. And that is one area that we really think we should put a little bit more emphasis on. So we have 2 people working on making it successful. And then we discuss what it takes to make it happen. Given the current environment where heterogeneous integration is a very important topic, we think having a chapter that describes interconnects is very useful to drive the right level of effort, both in academia as well as in the supply chain, to make a successful packaging envelope available to designers. Since this was the second chapter we released, we wanted to show that we are responsive to all the feedback we have received. We had quite a bit of feedback on the first version of this chapter in the 2019. We were asked to make sure that we cross-reference our numbers and correct them with reference to other chapters, which we did. So the numbers we present are consistent with what are shown in the package, the substrate chapter, as well as in the power delivery sections that use some of the characteristics. We had focused on forward-looking interconnect, and we had not paid as much attention to wire bond in the 2019 chapter, but in 2020 we made the wire bond section quite a bit more comprehensive by contacting lead wire bond suppliers, and we have included wire bonded stacks and their characteristics. We were asked to not just focus on package level 2D and 3D architectures, but also extend our work to wafer scale integration, especially given that Cerebrus announcements had happened in conjunction with our chapter release in 2019. We were asked to make sure we include it, which we have done. When we wrote the 2019 chapter, we had not comprehended we knew of a lot of announcements. I was part of the Intel announcements on a few new architectures such as omnidirectional interconnect and copper-copper interconnect. We did not include them in the chapter because they were not fully vetted out yet. But in the 2020 revision, we have included all those announcements. We also had accounted for what new product announcements like Cerebrus and their potential applications mean to interconnects, which we have done in the 2020. And then in parallel to the metrics we had described, TSMC announced a new set of metrics. We had not included them in the 2019 because they were not out, but in the 2020 chapter, we have included those. Additionally, the thermal team asked us to make sure we describe the impact of warpage on some of this scaling, so that this is not just a theoretical scaling, but it actually accommodates real life effects like warpage. And then we looked at socket trends, and we updated the socket trends in publishing the 2020 revision. This, I think, is what started the discussion, so I'd like to spend a little bit of time on this and explain the rationale for what we are trying to do and where it fits. So if you look at the history of packaging nomenclature, MCPs have been around for a very long time. Typically, they are side-by-side active silicon interconnected on the package. So they are called as,
Sorry, apologies. Do you prefer questions at the end or?
Anytime. You can stop me anytime. No problem.
All right, thanks. I just want to set the stage. That's all. Sorry.
Yeah, no problem. And in fact, I'd welcome any kind of feedback. So for some reason, this thing seems to keep scrolling at a certain pace. So 2D MCPs have been around for a very, very long time. And everybody knows that when you place silicon side-by-side interconnect on a package, you call it a 2D architecture. Somewhere in about 5 or 6 years ago, when HBM stacks, and before that the MC HBM, and there was another standard that had come out preceding HBM, where you had stacks sitting next to your compute tile. And because they were not entirely 3D, as in this was not a complete stack with nothing else, but it was a 3D stack sitting next to a 2D stack or a 2D configuration, people called it 2.5D, which made a lot of sense. And I've talked to Bill Chen about this, and Bill also agrees that the 2.5D nomenclature, which represents a halfway point between 2D and 3D, makes a lot of sense. But then a whole lot of marketing started. There was a 2.1D, there was a 2.3D, there was a 2.7D. And if you ask what distinguishes a 0.1 to 0.7 to a 0.3, you really will find there is no real logical or technical reason to distinguish them. It is just a marketing ploy. 2.1 is better than traditional 2. 2.3 is an improvement on 2.1. 2.7 is maybe potentially an improvement over 2.3 and 2.5. And then there was, of course, the standard 3D stacks represented by two primary memory stacks in the market, wide IO2 and HBM. And before that, there was the MCD RAM. So that was the logic. So the one on the left, reasonably okay. The one on the right, kinda okay. But the one in the middle was the question. And we were asked, is there a logical rationale on how we could distinguish those? So what we did was we came up with a new nomenclature that we circulated among experts for about 3 years now. The 2D architecture remains essentially the same. What you're doing is you're taking two devices. They could be logic devices, logic memory, or anything else. You interconnect them with the agency of a package. And these are what are called the traditional FCXGAs, the BGA, LGA, or the PGAs. Nothing changes in this definition. In the 3D, we added a specific descriptor. What we said was a 3D package is where active silicon is interconnected without the agency of a package, which means all the interconnects are built using fab-like processes, and they don't require the underlying package to create the interconnect between the active silicon. The stack itself can be connected on the package, but whenever you see a structure where there is pure interconnect between active silicon and doesn't employ the agency of a package, is what we call a 3D architecture. And then there is the most important in between. So we said anything that enhances the connectivity from a 2D traditional FCXGA, we call 2D enhanced architecture. Also, I should point out one more thing. When we talk about 3D architecture, we mean 3D face-to-back using TSVs. It could be 3D face-to-face, which doesn't always necessarily utilize TSVs. An example of a case where we don't utilize TSVs in a face-to-face is the POSSUM architecture that Amkor had publicized. And the 3D could be created using solder interconnects or hybrid interconnects like copper-copper. So all of them are within the descriptor of a 3D architecture. And now the middle. The middle is any enhancements in interconnectivity between traditional FCXGA. And you can always debate what does traditional FCXGA mean. So we described traditional FCXGA in the chapter. So any enhancements over it, we call 2D enhanced. And then we put a nomenclature that called 2D enhanced as either organic based or silicon based. And embedded within the descriptor of silicon is glass. If somebody wants to use a glass bridge, for instance, or a glass interposer, that is still a 2DS. And then in the 2D organic, we said you could have a chip last architecture, or you could have a chip first architecture where you could do reconstitution. Both of them essentially are 2D organic. So, if you use oxides or any kind of inorganic dielectric like they use in say hybrid bonding, that would start falling in the 2DS as opposed to the 2DO. And 2DS were interconnects where we formed connections between die using either glass or silicon. And this, Subbu Iyer pointed out, this should by definition say that this includes wafer scale interconnectivity, because you could have large interposers placed on top of organic packages. And this could be without TSV, like the current instantiation of the EMIB bridge, or it could be with TSV, as in a silicon interposer. This is
So Ravi, if you
yeah.
have an active interposer, it doesn't matter whether it is active interposer or passive interposer. Is that right?
No, active interposer, because it has connectivity that is without the agency of a package, it automatically becomes a 3D architecture. Like
Okay.
Foveros, for instance, Bill, if you took the Foveros construction and you put 2 chips on top, right? It is still a 3D architecture. It is no longer you're not using it just for interconnectivity. You're using it for functions more than interconnectivity.
And compared to that, we have the traditional package on package.
Yes.
That would be 2D enhanced?
Yes, it will be 2D enhanced.
Okay, thank you.
A good point. Maybe what we could do is explicitly call out POP in the 2021 chapter.
I think POP, package on package, is all over the place.
Yeah.
And I also see that the use of active interposer will increase. So these are 2 good examples that we want to put on the table. You should put on the table.
Yes, I will do that. I mean, I think it fits within the nomenclature framework, and this question has come up. The reason I had resisted doing POP, but which I don't think we should, is because it didn't have a scaling roadmap associated with it. But I think it's a mistake not to include POP, and it will be included in the chapter moving forward.
Thank
you.
So
if you have RDL interconnect, and that would fall, and that's without TSVs, right? So like ASC's focus or TSMC's info, those would fall into your enhanced architecture?
Good question. I'll show you examples of how. Yes, they will fall in the enhanced architecture, and I'll show you how we classify them, because Bill Chen had asked me to put in specific examples to explain the nomenclature.
Oh, great. Thank you.
Here, in fact, this is where, quote unquote, the rubber hits the road, right? So on the top left, you see the 2D architecture, which is a traditional organic package. It's a traditional organic package, FC-XGA, right? Where you do where you don't do fine litho or very fine RDL like TSMC is offering, very fine organic like TSMC is offering right now. Traditional organic is the MCPs we all know and have used for generations. Now take the FOCOS architecture that ASC offers. It is, in my mind, a 2D enhanced architecture. It is 2D enhanced because the feature sets it offers are better than what is offered by traditional packaging that uses nothing more than printing, like a high performance printing, but doesn't use enhanced litho techniques or anything like that. So it becomes a 2D organic, 2D enhanced 2DO architecture. Similarly, if you use TSV, as Bill was asking, it still is 2D enhanced for the same reason. We are not doing interconnectivity of active silicon without the agency of a package. We are interconnecting active silicon with the agency of a package. So it is a 2D enhanced architecture. Wafer scale is an interesting case, but you could argue that the wafer scale constructions that are being promoted by UCLA and by UIUC use just larger and larger base interposers. They are not doing anything more. Like, in other words, they are not putting any active circuitry in the base. They are just connecting using the interposer. It still forms in the 2DS category. Similarly, the 2DS with TSV is what is used, that's CoWoS. So CoWoS and wafer scale are different only in terms of size. Just like that, the EMIB architecture is nothing more than a 2D enhanced architecture. It is a 2DS without TSV, right? There is no TSV interconnect to the package. And then the last one is the face-to-face architecture represented by Foveros. This goes back to the question Bill was asking. Now it's an active interposer. The base is actually doing much more than just offering interconnectivity. It is offering functionality. and there is no agency of a package. We don't go through the package to form the connection. You could argue that the POP does it and that the stack connects to the package, but the connectivity between these two entities is 3D. So this is what I call a 3D architecture. It is face-to-face. Does this make sense? And the question we have to do is continue to both explain this correctly and make sure that the nomenclature we offer is completely representative. It is quite possible that we may be missing some cases or have blind spots. I haven't identified any yet outside of the POP, but I would love to get feedback on whether this nomenclature makes sense.
Sorry, Foveros is only F2F?
Right now, Foveros is F2F. It doesn't have to be F2F. Like if you take a look at HBM, HBM is face-to-back. Foveros is face-to-face.
Then you mean Foveros cannot be used for HBM, or can be?
No. Foveros and HBM are two different applications. HBM uses face-to-back and Foveros uses face-to-face.
Thank you.
HBM is memory on logic. Foveros is logic on logic.
So the way you define 3D is essentially when any of the connectivity between chiplets is through the wafer.
Doesn't use a package.
Doesn't use a package. Okay,
correct.
Yeah, that's a better classification. Okay,
Yeah,
understood.
Yeah. Otherwise, you get into all kinds of logical problems.
Yeah.
I think, Ravi, sometime soon we would have examples on the on co-packaged photonics, and at that time we'll see how it works out in this definition.
Yes, so Bill, I can tell you based on all I have seen to date. In the case of co-packaged photonics, there are cases where the photonics IC is directly connected to the package, or the photonics and the electric IC is directly connected to the package. If you look at the IR announcement at Hot Chips, no, not at Hot Chips, at OF, I think, optical fiber, OFC, they are strictly 2D enhanced. They use an EMIB based interconnect. But there are cases that people have talked about where they disaggregate the electric IC and the photonics IC and they stack it. It then falls in this, depending on what interconnect they use, whether they use a EMIB or a CoWoS, it could fall in the 2D enhanced category. But I agree with you. We will have to look at all the cases for optical and make sure they fit in this nomenclature.
Sorry, just because you name IR Lab is monolithic. It's not 3D integration. Just wanted to clear.
Yeah. So let me explain what I meant by IR. What IR Labs is doing in the demonstration they did at OFC is a monolithic optical chip connected to a FPGA using an EMIB bridge. And that's what I meant. The interconnect is 2D enhanced.
Yeah, correct. Thank you.
2DS without TSV. The IR Lab, you're right. The logic is the optical and electrical logic is monolithic. So this was the nomenclature story, and I would welcome any kind of feedback. I should also point out that there is no intent to compete in any way with any marketing directions that a company may choose to employ. The idea is to offer a framework for everybody who writes technical documentation to communicate using a common description.
Is there a established relationship that the greater the number, likely the greater the current cost?
Greater the number.
I mean, like you go from 2.1, 2.73. That
Oh, I see. No. There is good question. No, there is no. Like you cannot automatically assume that 2.1 is cheaper than 2.3.
I see. Okay.
You cannot, because the cost is. That's a good. Yeah, I don't think there is. No, not only. I shouldn't say I don't think. I know there is no direct correlation, because there are intertwined relationships of yield and volume that are independent of how you call it. So you cannot automatically assume just because you are buying 2.1 from somebody, it is cheaper than buying a 2.5.
That's a pity. It would have been nice.
It would have been nice, yes.
Greetings, by the way. Do you have some reports on the yield of different packaging solutions?
No, there are studies that have been done. For instance, I'm sure TechSearch will have something, and I have seen a report from Yole on yield. And associated cost. Yole and I'm sure TechSearch have something, but we don't. Outside of pointing out that there is a need to focus on yield, we don't get involved in commenting on yield of different technologies because there's too many non-technical issues associated with it or intertwined with the technical issues.
Thanks.
I think following what Ravi just said, I think I think we do not want to be part of the reverse engineering cost analysis that Yale has, because this is a money-making operation for them, and we need to stay out of that.
Yeah, absolutely. Let me talk a little bit about metrics because this I think is very important for making sure that roadmaps are done right. So if you look at the role of a package, okay, as all of you know, bumps on the die connect to pads on the package, and they offer interconnectivity. In case of 3D stacks, bumps on a die connect to bumps or pads on another die, and they offer interconnectivity, right? So at a very high level, the role of a package is to do interconnect scaling. If interconnect scaling happens in a package as described at the top, where connections from the die are spread out laterally in a horizontal plane and they escape the edge of the die to form connections to another die on that package. The metric you care most about is how many wires do I get? And you have to be careful with defining the word how many wires, because if you continue to add layers, you will get more and more wires, right? So you have to normalize with reference to the number of wires, and you have to normalize it with reference to die size, so you're not die size dependent. That comes up with a very simple logical construct that says number of wires per millimeter of die edge per layer of the package. For some reason, a lot of people use the word I/O when they talk about physical interconnectivity. So the word I/O is oftentimes used interchangeably and sometimes misleadingly, because if they don't account for sideband, you get a very different number. So we highlight that we are talking about wires that escape per millimeter edge of the die per layer of the package. And then we also highlight that you care about bump density, which is the number of bumps or I/O per millimeter square. And these are the two metrics, I/O per millimeter and I/O per millimeter square. Last year, actually 2 years ago, Doug Yu gave a talk at IEDM and followed it up with a talk at the ECTC, in his keynotes, in which case he took the same metrics and he multiplied the two. So he took the I/O per millimeter or lines per millimeter and multiplied it by vertical interconnects per millimeter square. So both these metrics are consistent. You can either keep them independent, which makes sense when you do peripheral interconnect, or you can combine them, which makes a lot of sense when you do direct vertical interconnect. Okay. I should just highlight that in general, both metrics are exactly the same. So if you accept that these are representative interconnect physical metrics, then we can start constructing a roadmap, right? But before that, let me back out. Essentially, packaging offers 6 types of interconnects. It offers die-to-die interconnects, which are interconnects between stacked die, and they are covered in our chapter 22. It offers on-package die-to-die interconnect, which means these interconnects do nothing to escape signals from that die to the outside world. They just connect die to die. These are covered by 2D and 2D enhanced interconnects, and we have a roadmap for how these interconnects scale. Then you have the die to package interconnects. What these are is a combination of both interconnects between die and interconnects that escape out of the die to the external world. There are within package interconnects. They are not covered in our chapter because it makes a lot of sense to cover them in a package substrate chapter. But we have established consistency between our numbers and their numbers. And
so
then there are the
Ravi, this is the single and multi-chip package, including substrate.
Exactly.
That's a chat. So maybe you could add that number in your
I should add the chapter number itself.
Yeah.
Okay, I will do this.
So Ravi, the within package interconnects, that is connectivity to discretes or on the package?
It could be connectivity to anything. Like it could be connectivity to discretes, it could be connectivity to active, and it could be connectivity that allows you to escape out of the package. So whatever interconnect transformations or scale transformations you offer or space transformation you offer is within package. Anything that is done entirely within the package is what we call within package interconnects.
Okay, understood. So, thank you.
Right. And then we have to connect the package to the board or daughter card. It could be anything. We cover those also. And they are, as you know, 3 classes. There is the ball grid array, the pin grid array, and the land grid array. And we covered those. We focus more on land grid and ball grid because pin grid arrays are around, but they are not evolving, if you will. Okay. And then the question Bill brought up, this whole thing of package on package. And I should point out that there is no natural scaling to package on package because it depends on the memory, which is primarily what they are used for, but it could be used for something else. The memory connectivity demands and also the Z height demands. So what we decided to do was to capture the best known information available and explicitly state in our chapter that this is not a roadmap, this is a current snapshot of the current state of the art. So 5 out of 6 are covered in this chapter, and we are consistent with the 6th, which is in another chapter. I was kind of glad to note that we did not change the tables much in the 2019 to 20 chapter. So let me see if I can explain how these tables are created. The whole idea of developing interconnects on a package is to be able to offer better and better performance. And the one performance metric that seems to be the most demanding is bandwidth. So we ask the question, if independent of protocol or anything, if just raw bandwidth is used as a metric, which is number of wires multiplied by signaling speed, and if we give ourselves the goal of doubling bandwidth gen over gen, and if you ask where does the word doubling come from, there is an IEEE projection for SerDes which claims that every 2.1 years the bandwidth doubles. So we use that as a basis of our definition of generation, the doubling. And we said, let's start with looking at peripheral interconnects and let's look at aerial interconnects. So let me start with the peripheral interconnects. We decided to actually no, this has only aerial. So let me talk about aerial. WideIO2 was the first known instantiation of aerial interconnects. It was at 40 micron pitch and it offered a raw bandwidth of 125 gigabytes per second per millimeter square. It was accomplished using the 40 micron pitch and a signaling speed of 1.5 or 2 gigabits per second. I should point out. Yeah, go ahead.
Quick question. These are micro bumps, right? This is not C4 bumps.
These are micro bumps. Yeah.
Yeah. Okay. Thank you.
That is correct. And I should also point out one more thing. These are non-unique. In other words, you can achieve the bandwidth density by different combinations, and people do achieve bandwidth by different combinations. We picked a representative combination to show how they should be done. So you could pick a scaling roadmap. So if you start with generation 1, then generation 2 should have a doubling. You can change vertical interconnect density either through solder, which is a slow change, or you can do it with very aggressive transitions to hybrid bond. And that's where the economics comes into play. So we didn't want to play decision maker, we represented both. So we said if you take bump pitch and you shrink from 40 to 30 to 20 to 15 to 10, somewhere in the 20 to 15 is where the transition from, or maybe even north of 20 is where the transition to from solder to hybrid comes in, and you calculate the aerial escape density, you could calculate the capability of the technology, you could prescribe a speed. It is not a unique speed, but you could prescribe a speed which will allow you to double the bandwidth. Okay. We put in the number of 4, but we also said that was clock rate dependent. So this gives you a physical scaling roadmap. And I was very happy to see in a presentation at Georgia Tech that they had taken this roadmap and they had actually shown how you can go to 2 to 3 more generations and continue to double the bandwidth. Really, that gives you basis for saying you have a really good roadmap that allows you to project for the future. The next question we asked is, the IEEE projection says every 2.1 years, but reality is all kinds of economics will play into when you transition. It's not just the interconnect scaling. So to make a sort of broad generalization of what is a generation, we said a minimum of 2 years and technically a maximum of 3 years. Economics can delay that, but we said between 2 to 3 years would make a lot of sense. This just allows you to calculate how much time we have to get ready for, say, generation 5. Okay. It is possible you may be early or late, but at least it gives you a map of how to be ready. Okay. Does this make sense? And our goal, we learned from ITRS, so our goal is to continue to change this to adapt to reality. I'll also show one more table which is important. We are talking about scaling of interconnect and enabling this. To do this, the one thing that truly matters is bump capacitance. Other things matter as well as R and other characteristics, but they depend very much on how you scale the physical interconnect. But we said to hit this, we have to continue to target reduced bump capacitance. And we put this in the roadmap to show what it takes to hit bandwidth doubling. Okay. And again, as I said before, we always welcome feedback on how to change this should it need to be changed. Any comments or questions on this?
Hey, Ravi, I have a sort of a unrelated question, I guess, for lack of a.
Go ahead.
How do passives fit into all this? I mean, the sort of the last line of bump capacitance sort of caught my eye.
Passives do not fit in here because all the interconnects in this particular case, the interconnects we are talking about are enabled either by on-die capacitance, but we are talking strictly about the link. That's a,
not just this slide, but I guess in general, like, when you're talking about packaging generations, etc., do passives, is there a separate access for passives, or they just sort of exist in?
We did not include it here because that's a pretty difficult question. There's one more thing in addition to passives. The other question that I guess people automatically ask is, where does ESD fit in all of this, right?
Right.
Because they relate to power capacitance, but you see those are not roadmaps that the packaging guys alone carry. We may influence the supply of passives or the attach of passives, but we don't control the demand. So we deliberately stayed away from passives, inductors, and resistors. You are right that there should be a passives roadmap, but it didn't seem to be a natural part of the interconnect roadmap. Does that? It's not a cop-out answer. I had thought quite a bit about whether we should include passives.
Right. It was the passives, power, and ESD are the ones that people keep asking about.
Yeah, but they are, ESD should realistically be covered in either the reliability or the manufacturing chapters. I mean, I have an opinion on ESD, but I wouldn't want to put it in an interconnect chapter. And passives is, there's a supply chain, and then there's a powertrain, and there's an IO performance roadmap that they have to be tied to, which is not entirely within the domain of packaging. We own the supply, but not the demand. So we also listed in this, because it is all relevant to the interconnect enabling, what are the difficult challenges. One difficult challenge clearly is, as you shrink features, you have to pay exquisite attention to signal integrity. And I don't think there is a case where just because we shrink, we are allowed to escape the bandwidth. So we tried to describe how to double bandwidth with shrinking of interconnect, but we have to have co-design tools that allow you to study signal integrity when you shrink features. The second is assembly of solder and non-solder interconnects. Copper hybrid bonding will require a different class of assembly compared to, say, solder-based interconnects. Solder-based interconnects, as they scale, will require a different level of attention paid to their formation. Sort and test, especially at fine pitch, will require strategies to keep up with the pace of interconnect scaling, or they may delay or impact at least the rate of scaling. We pointed out that just because we scale interconnects and bring things together doesn't mean everything is good. Thermal management will become a big problem. I shouldn't say become a big problem. Thermal management is a big consideration when you bring things together. As you bring different entities together, power delivery networks have to be both decoupled from each other and they have to become increasingly efficient. That is part of the power delivery chapter, but we do point out that interconnect designs have to accommodate for the need for discrete power delivery networks. All of this requires significant co-design, both for process and design. And this is a pretty intertwined thing, but we pointed out that there is a need to do both. And the last is the reason why we emphasize the time vectors in all of our tables is because equipment has to be ready for any of us to hit that the times we prescribe. You have to have equipment that is ready and available broadly. So we pointed out that there needs to be a synchronization of equipment readiness. In the 2021 chapters, our plans are to improve the images we have put in. Our plan is to continue cross-referencing with other chapters. We believe we have done enough, but the other chapters are also evolving, so we have to continue doing this. We have to recalibrate on the projections. Either they may be too aggressive. For instance, as you double SerDes speeds, it's not natural that they will keep hitting the 2.1 cadence. And we have to refine our roadmaps according to that. We have to also keep in mind any industry announcements. Bill Chen pointed out photonics. We have to make sure that we understand the impact of photonics interconnect on this. And we should include work done in universities. We've done a pretty good job, I think, of including whatever work is done at universities, but we have to keep up with this. And we are always open to other suggestions. Okay, so this is my last slide. We updated a chapter and we released it. It is in peer. We actually had done a very thorough peer review. We got some really, really good feedback. And so quite a few people contributed. I'd like to thank them, and we always welcome new participants, and we are in the process of writing the 2021 chapter. So that was it, Bapi.
Thank you. Any more questions for Ravi? So I've got one last, at least at my end. What did you and and Subbu and the group imagine as a sort of the before and after of the chapter, in the sense that how does the chapter get consumed in your thinking?
I will comment, and I'll ask Bill Chen also to comment. In my mind, what this chapter does is provide a framework for how interconnect should evolve and why interconnect should evolve. In doing this, we point out that there are quite a few things that have to be done. There are significant integration challenges, materials challenges, modeling challenges, and equipment/process challenges. By highlighting a roadmap, we are hoping other people get aware of this and will plan to make these things happen. We are also hoping that some of these things get distilled into research challenges, which will get funded through whatever level of federal and industrial funding is out there. And to do all of this, what we are doing is we are presenting these in HIR workshops at different venues, so people are aware of the work we are doing and they recognize that there is a need for everybody to come together and be successful. And I'll ask Bill Chen if he wants to add more to this.
Yes, and I think, Bapi, just like the presentation that I gave on Wednesday, the purpose that we have is to have this kind of document. This is one chapter. We have other 22 chapters. And the purpose is to put that in front of audience such as this today, so that we could have this information on the table, so that we could propagate this information, all of us learning together. The second thing, as Ravi has mentioned, is that we want to put this in front of the funding agencies, such as in SRC, and opportunities such as now with the U.S. White House announcements about the funding to go to NIST. We think that if we can use this document so that the funding agency could look at and said, yes, the difficult challenges that is described there does make sense, and how does the research go forward? The equipment manufacturers look at that and say that, yes, we need to develop equipment for the next generation of equipment to go to the industry. We talk about equipment, we talk about materials, materials developers. What comes after hybrid bonding? What is the next one that would come that would give us a final pitch? We don't know, and that is where the research comes in. So that's the purpose of our roadmap.
Yeah, it's like the ITRS, except at a much grander scale, if you will, because the scope and diversity is much broader.
Yep. Okay. Just one of the interesting things, at least I've seen in the ODSA and I've in a couple of other places, is how to translate this information into something that system designers understand.
Yes, yeah, good question. What we are trying to do really is to make people aware of this, and maybe part of this could involve a translation. By the way, we are already finding, I shouldn't say we are finding out, we knew this for a long time. The language we speak versus silicon layout people is different. So our code design tools operate on a different language. I think you will see that the same will hold true between the packaging and the system groups or the IO groups. So there is a certain language differential or barrier or differential we'll have to navigate through. I mean, I pointed a very simple example, use of the term IO. We talk about wires, people talk about IO, and sometimes the two are equal, sometimes they're not equal. So we try to bridge that gap. That's a very small, non-trivial example, but there's many like this. But you're right, there is a lot of translation that needs to happen.
I want to add the word that when we talk about co-design, I think the 90% of the people that heard the word co-design thinking that it is co-design, electrical design. And in the true sense for chiplets, when we are dealing with more than 2 dies, co-design must contain thermal, must contain mechanical, and so the word co-design becomes physical design and would involve a multidisciplinary approach.
Okay. Any other questions for Ravi or Bill? Well, thank you for your time, Ravi. I'm glad.
Sure.
Many thanks. Sure. And thanks, Anu, for setting this up.
No, absolutely. And I think at ODSA, we just adopt these, at least the nomenclature standards, because the division within the 2D enhanced space is really, it's a marketing thing, and it gets quite painful between different companies who make this stuff. So it's a lot easier to just keep it as 2 broad categories and fit pieces under those categories. So yes. I believe this is the way to go.
Yeah, and I should point out that in doing so, you will, I'm sure, find cases where this doesn't work. I would love to hear what that is. Yeah, so that we can continue to enhance it. There is no claim whatsoever that this is complete. We are getting as much resonance as we can.
Right. Thank you, Ravi. Appreciate it.
Sure. Thanks, folks.
Okay. Thank you all.
Sure. Bye.
Bye. Have a good weekend.
Yep, you too. Bye.
Sorry
This
about that.
conference will now be recorded.
No worries. All right. Hello, everyone. And the agenda for today, I'm just focusing everything around the OCP Tech Week and what will be the contribution from Chiplet Business Work Group. So I have lined up three discussion and like mainly those are follow up what we discussed in the past. So I'll start with the known good die use case scenario modeling talk, which Roberto will share the outline and how he's thinking from an abstract standpoint. Last week when we met, we thought should we do a panel rather than a talk. So he and I had some discussion, and I think we both feel there are a lot of panel has been done in this space, but every time we have a panel, it's string of opinions that people share. But I think here what we are trying to do is go past from opinion to some kind of a work which we can contribute to the community. So Roberto will have a outline how he's thinking, and then we can have a more discussion. Will that work for everyone? Go ahead, Roberto.
Yep. Thanks, Ravi. Let me just share my screen. See if I can share the right screen. Okay. Let me make it a little bigger. Yeah, I think Ravi did. We did talk, right? And if you guys think it merits a debate to see whether we want to do a presentation or a panel, I'd like to hear the alternative if a panel is of more interest. But I think we just, to Ravi's point, we kind of converged on presentation. It'll really it'll force people to kind of get out of the opinion mode. Panels are interesting, right? It's different opinions from different perspectives, right? So it's opinions from people maybe coming from the test and package, people come from the design side. But I think a lot of that stuff has been said time and time again. And the idea here is see if we can put a little more teeth to it and kind of move the ball forward from the economic model perspective. So I think if you guys can read the abstract, having me read it to this group might not be the best use of time, but if you guys can read it, so I'll pause for a minute or two. This is kind of my thoughts on how we'd approach a presentation, and then I've got some comments around help needed. Maybe we can have a discussion around that as well. So I'll pause.
Is the question whether there should be a panel or a presentation? Is that really what it is?
Let's see.
I think go ahead, Roberto.
No, go ahead, Ravi. Go ahead.
So Anu, I think first is again our recommendation is it should be a presentation, and which we are open to have a discussion and get everyone's perspective, because we had several panel in the past in different forum, whether it is ECTC or whether it is even OCP Tech Week last year. So the thought process is like what even you, Mudassar, and Javi are trying to do, developing a cost model, which means we are adding content to the community so that people can use some of those things as a reference. Along those lines, so the thought process, even for known good die, we will use as a system in package as a business model, and then do some scenario planning for 2 chiplets or 3 chiplets, something like that, and then come up with some known good die challenges and how it's being done, so that we can add some information which community can use in future. And what Roberto is sharing is an abstract of his thought process, and he's asking if there is any feedback or should we even do a panel rather than a presentation. I think that's pretty much high level.
Okay, thanks.
Ravi, one of the presentation from AMD at the ECTC keynote, they are talking about in a wafer you have die which is some die which is faster than some other die, and so they put that up as being a question because they were saying is that they do not want to sell the die or sell the chiplets that is at the lower part of at the lowest part of the spec, because the spec would be the lowest to make all of them to meet the spec. It would be the lowest, the slowest. But so how do they make use of, take advantage of those that is higher performance than the spec would be a question. I think this is not a definition, but I think this is a point that you might want to include in your presentation, include in your discussion.
So I have a quick comment on the presentation, which I'm reading on the screen right now. And the comment is as follows. All of the thing which is written in the abstract holds true for any type of chiplet-based systems developed, whether proprietary or open. I think we need to sharpen this a little bit further to emphasize what is it from the open ecosystem perspective where we need to work on defining a known good die issue. So as we know, known good die problem is already solved in a proprietary ecosystems, whether companies like NVIDIA or AMD or Intel are putting systems together, they know how to manage this problem already. What we do not know is how would this work in an open scenario, such as what we are trying to do in ODSA. So I don't see any emphasis on that side within that abstract. And I think we should probably try to bring that part of the problem out very crisply, so that what kind of information needs to be exchanged across vendors in open fashion. Are there any hesitations across the vendors? And I think some of these things are precisely what we discussed in the business workshop in March. So maybe we can kind of use some of that, revisit some of those conversations from that workshop and bring it into the abstract here. So those are my quick general observations.
Thanks, DJ. Go ahead, Anu.
So DJ, I think he's got this statement in the second paragraph. He says, propose an example known good die agreement between SIP builder and chiplet provider. So that would be a really good basis. And this could work for, vertical integrators do whatever they want to, but this could work across the board for different people. So I believe this is sort of a start of the direction you're talking about.
Along those lines, DJ, if you read in the second paragraph, it says to promote a model that encourages multiple vendor in a single package. I think multiple vendor by far, I think it's not said open clearly, but I think that's what intent is. Roberto, correct me if I'm wrong.
Yeah, no, that's the. I think. Well, first of all, thank you, DJ, for the feedback. Yeah, the intent is exactly what you said. I took a note, and maybe I need to read it with a more critical eye to see if maybe we need to be more. I tried to be explicit, but maybe it just doesn't jump out. But that's absolutely the intent.
Yeah, I'm just playing devil's advocate. I mean, I completely understand the message in between the lines, so to speak. Multiple vendor. I completely get it.
Declare it,
right.
Declare it earlier and more often.
Right. The litmus test I'm using is very simple, and you can use that litmus test. The litmus test is, if you are running a proprietary ecosystem, all of these things, what you have written, hold still true. All of them, right? If I'm a proprietary vendor doing multi-vendor in single package, I need to have an agreement. I need to do all of that. It goes without saying, right? So litmus test should be, can we have something which doesn't apply to a proprietary ecosystem, but which is unique to the open ecosystem? And that's the highlight which I'm trying to grab at, is what is, let's say if NVIDIA is working with two chiplet vendors, they are also doing multi-vendor integration, and they are doing things in single package. They are also coming up with an agreement of known die between a SIP builder and a chiplet provider. All of that is still happening, mentioned in the second paragraph. So the sharpness which I was thinking of is, so what is it unique about open ecosystem which doesn't apply to the proprietary ecosystem? And that's where we put our focus on.
So you will have a sentence or paragraph that represent what you just said. The difference between a proprietary ecosystem and a open ecosystem. You want to discuss that. That was a very important point to discuss.
Correct. Exactly. Yeah. Is there something unique? Like, what is it we need to solve in open ecosystem above and beyond what people have solved in the closed ecosystem? That's what I'm trying to say. We can solve it in closed ecosystem as a regular business day in and day out. Obviously, there's no open ecosystem, so there are some other challenges which are there. Maybe companies are hesitant to share some information in open. Maybe there's IP exchange, which again, those are the things where we can focus on the discussion, because until those are solved, open ecosystem will not be realized.
I think it's an extremely important point, because today most of the chiplet work within AMD, Intel, and it's very different because they are very much closed.
Great feedback. Any other input?
I'll also publish, maybe Ravi, you and I can follow up. I don't know where to, maybe I could just email it to this group after the call if you guys want to sit on it and send me back some feedback, or if there's a document repository that we normally put stuff up, I'd be happy to put it up there too.
I think Javi is trying to say something, but we can't hear him. So is he still on?
He is still on, but yes, we can't hear him.
Yeah, he just sent me saying, I'm trying to speak. Why can't anyone see me?
Oh, he thought we were being rude and just speaking over him.
Exactly.
Yeah. His mic's not working, I guess.
Maybe he can type his question, Javi, and we can read it out in the chat as an option.
So is this any better? Can you hear me?
Yes, we can hear you.
Oh,
okay,
yeah.
Great. Yeah, that's exactly what I was thinking. I was trying to interject and I wasn't able to get a word in edgewise. So a question comes up with KGD, and this whole chiplet business is really tied to economics, right? Because you're trying to find a less expensive way to get into a market, but KGD can mean a lot of different things. And if you take the extreme, kind of like what automotive products are with their definition of KGD, that last few percent of test coverage is incredibly expensive, right? Because you've got to make sure that absolutely nothing that fails can make its way through. Where there may be something prior to that that is far more economical and at least good enough to get into the next step, a certain amount of coverage and a lower amount of risk, but not exorbitantly expensive. And defining that may be a very high value rather than saying it's got to be absolutely good, because then it becomes considerably much more expensive.
That's an excellent point. And I've got this whole, I've started to model a little bit, to be honest. And yeah, it's what's good enough, I think, is maybe another way to say it. I think to say it has to be 100% perfect is not really achievable with chiplets. And so what my ambition here is to actually declare in under certain examples, right? There's if you think of all the permutations of a chiplet, there's going to be many of them. But if we can, that's why maybe get into the help need. If we can pick a couple of chiplet examples where there's maybe it's two chiplets and there's one vendor, and each, one vendor provides one chiplet, other provides another one, then you can maybe you double, you go to 4, and then you go to some other number of combination. It's almost with those examples to declare what we think is what's good, declare it from a yield perspective, and in a manner where the chiplet provider makes money and the builder makes money as well. So I've got these strong ambitions where we can and I think it'll be good to declare something. And that's why a panel will just give opinions. But if we can push the ball forward with an economic model, then I think we'll more likely to get feedback on whether that even makes sense or not. Is if we can be so bold as to declare what's good enough. Does that?
This is Elko. Sorry about the background noise, but just a thought. I mean, I totally agree with Javi's statement, right? It's the 80-20 rule or the 90-10 rule applies. You're going to spend the bulk of your money on that last little bit. So one question is, what's good enough coverage? But another way to look at this is also to look at the chiplet functionality and basically say, okay, at what level of functionality are the test yields good enough, or can the device be tested to acceptable KGD levels and still achieve reasonable cost? In other words, a SerDes interface die, you can get pretty good yields, pretty good KGDs, but if you try to put too much logic on the die, then you may hit a point where it starts to fall off. So that might be another interesting thing to look at from an economic model perspective is, what type of functionality will allow you to achieve the KGD levels at reasonable cost.
So may I suggest something here, because the intent today is just to share an abstract, and then and we are now, I think, getting into a little bit more on the solution side. So definitely Roboto will need help from the community to move forward with even, with this analysis. So I would like to ask for some, help here and see who wants to volunteer, so that we can, like what Anu, Javi, and Mudassar is doing, where they are developing this cost model, working with Elko and Swami in offline mode. So likewise, I'm looking for some volunteer who can help Roboto with this kind of analysis.
So I'm happy to help Roberto from some of the comments I brought up on the KGD. So I'm happy to go and work with him to see how we can incorporate some of that thought process. So, and I think, Roberto, we probably need to complete this submission before the end of Friday, right? So,
Yeah.
So I think we can try to close it on by Tuesday, Wednesday latest. And I'm assuming we are doing it through BAPI, or we can do it on our own as well. But let's work on this together Tuesday, Wednesday next week. I'm out Monday, hence I'm suggesting Tuesday, Wednesday. And we probably need an hour to kind of, finalize it. And others, anybody else who wants to join?
I think, DJ, you're referring for the abstract. I was asking for more, the body of the work.
Yeah, so what I'm suggesting, Ravi, is because the abstracts are due next Friday, maybe for today's call, let's just focus on that, because after 23rd, we are gone. The timeline is gone, right?
Yes.
And then we can always talk about body of work, even, next Friday or the Friday after as ongoing. But my suggestion would be we be very tactical for next 38 minutes or so to knock out the OCP Global Summit submission, because I'm sure there are a lot of questions coming up.
By the way, how much time do you have for this presentation?
I think I have a question for Bapi. Bapi, is there a limit like 10-minute, 20-minute, or what's the?
Well, I think it's going to depend on what the whole set of proposals come through, and then we're going to have to. My sense is it's going to be very difficult for us to justify more than a day's worth of talks. So
yeah, my suggestion would be we should earmark two types of talks. Essentially, one would be lightning talks, which could be 5 minutes, and one would be a longer talk, which should not be more than 15 minutes at the max, or maybe 20 minutes. So we can consider this online of a little bit of a longer talk. So maybe 15 to 20 minutes.
Hey, I've got to drop at 9:30. Ravi, may I ask you something quick? I apologize for interrupting the flow.
Sure.
One of the things we had this really fantastic workshop. I mean, we had something like, I don't know, it's 500 people at one point registered or something, and then at least 300 logged on. We don't have a place where sort of done here's the key points, lessons learned, and not from the workshop. It would be really nice to have at least even a PowerPoint deck, if not a document. Because otherwise, I think the workshop is lost to memory, and I'm really worried about that.
So, Bobby, I'm glad that you brought it up. So maybe we can do like a 5-minute lightning talk for the work group update, and then I can, work with DJ to summarize in a few slides.
I'm thinking sooner, just to okay.
So that
not
will
just
be
in November. I'm saying before that. Hopefully in the next month or so, to have something tangible which we can say, here's the considered wisdom of the group, and then you can do an update in November.
Okay.
Anyway, that was my one thing. It's like I was preparing for the MEPTech talk and suddenly realized that there wasn't nothing we could sort of say, hey, here's what happened. Here's the wonderful stuff that happened.
So you are saying maybe we should do a interim update in the 8 a.m. call. Did I get it right?
No, not an interim update. I think we need. Okay, I'll give you we need something about this is the consensus view that emerged from the workshop. This is the
okay. So Bapi, yeah, sorry to interject. Basically, what you want is us to distill a summary of what happened in workshop via a bunch of slides.
Yeah, not a sort of a business summary, but more but
no, not a business summary. Basically, summary of key things, key learnings, key insights coming out of bubbling up from the workshop.
So where do you want us to bring this, Bapi? Maybe that's where I'm not getting it.
Two things. One, it is possible. I think your idea of doing here's what we learned at the workshop in our Friday meeting is a good thing. The second is, if we have volunteers to write a document, there's probably many places we could go hunting to publish this. I think that's it.
Yeah, I think, Ravi, I understand what Bapi is trying to do. I think this is probably germinated based out of his initial request. Hey, do you have one slider on what happened in workshop? I think that's the original thought which is causing him to think of. So let's create a canned presentation which everyone can use as what we accomplished out of workshop, which the community can use, highlighting quick summary of the workshop with key insights.
But I think DJ Bapi is asking two things. One, a summary of the workshop, but after all the work we did, where we converge as a community into few problems and which we are now working and driving as a part of this post workshop.
Yeah, this is my suggestion. I'm wondering whether all of you on the call think it's a good idea, because it feels like, there's a lot of work which isn't being referenced.
Bapi, I think this is how we should parse it. We should separate the two. I think the work which community is doing, I think we can come up with it over next 3 months or so, because that's an ongoing effort anyways. I think the workshop thing is important because like you said, it's a lost memory. The further we move away from March, I think the weaker our memories will be. So we should capture that as a immediate step, and then work of the community. We can capture it to be presented, like Ravi said, in lightning 5-minute talk at OCP Global Summit.
Makes sense. So take the workshop, summarize it, and then say here's the key agenda action items
Exactly.
we took, and then and say here's where we are, and that's an update to the group, and we find some other way to publicize this work as well.
All right, sounds good.
Okay, thank you. Because it's pretty important in my mind to sort of disseminate whatever we did.
Yes, and what we are working on, actually, like not what we did as well as what we are working on now, both.
Yeah.
Okay, I think that's a good point.
Thank you.
Thanks, Bapi. So I think before Bapi brought this up, we were asking for volunteer. Anybody else wants to volunteer for the abstract next week? Right now, I have DJ, and again, I will be also plugged in with this and Roberto. But anybody else wants to join for next week, if to tailor this abstract or for the body of the work, which we can discuss later as well. Okay, if anyone has any interest, either email me or DJ, and we will pull you in. Otherwise, for now, if no more question or comment on this topic, I would like us to move on to the next topic, which is a proposal we discussed last week from Kevin and Rishi on open interfaces use cases and a panel structure. So Rishi and Kevin, do you want to share your thought?
So, Ravi, this is Rishi, or maybe if Kevin or you can share the slide. I have a little bit of a problem with my machine and this platform. If you please can share it, that would be nice. I can speak about it.
Kevin, do you want to share or you want me to share? Because I'm assuming Rishi is the same deck
Same deck which I sent last night.
Yeah, okay. So let me just.
Ravi, there's fine. If you have it, it's probably easier for you to share since you have control.
Yeah, let me share. Okay, if you guys can see my screen, do let us meet. Okay, you guys can see my screen?
Yeah. So, so guys, I've just used the Cadence template, nothing to be specific about the company or organization I work for. This is just an open forum, so I'm just giving a disclaimer that I'm not trying to pitch or sell anything specific to Cadence over here. Okay, next slide, please. And Kevin and me have jointly reviewed this. So the concept what we basically wanted to get over here is, this is no news for any one of us over here in this forum, that chiplets is basically being used, and there are different verticals which we have kind of subdivided where the chiplets are being deployed in our use case for silicon design. It can be a processor intensive application where it can be multi-core GPU or a CPU with a workload accelerator, or even for scientific computing where you have something like sparse matrix or a vector scaling being associated with a CPU engine. The second case is more taking on the memory side, since most of the processing for edge compute or AI ML is dependent upon memories and how the cache management is done or cache extension. So chiplet becomes very key for memory storage extension or memory application, and even for 5G as a matter of fact. And people are looking up at it for packet buffering and lookups for network or NPU class of applications. And when there are heavy data analytics where you need to go ping pong the normal conventional DDR or a memory module sitting outside, doesn't scale so well with the CPU performance, and people are looking at options for storage or memory in chiplets. The last is basically taking it to the complete frontier of connectivity, where people are trying to optimize the whole system cost by integrating multiple die into one package. And this is more a humble concept of NOC, where previously it used to be within an SoC, but now it's coming into the die as active interposers. And people are also using it, or folks can be more creative of doing it into a full-fledged server CPU, where you integrate multiple IOs, a classic north bridge, south bridge, or even the platform host controller into a single SoC. And all these three verticals, if you look at it, kind of diversifies or gives different verticals to the chiplet PHY by itself. And that's the theme where me and Kevin were trying to bring up, that the PHY application is one for all, will not fit into a chiplet deployment. These are all chiplets, but the use cases are pretty much different. So if you go to the next slide. So here I've given an example of processor, a CPU class example, and over here and even within CPU there are different breeds where you can do homogeneous and heterogeneous. The way homogeneous works is a classic example. I'm giving public information sharing over here, is something which AMD did in the first generation. Multi-dies of a certain amount of CPU core, 4 or 8, and then you scale that with a common fabric and get from a desktop to a server class CPUs. A classic example is Rome. And when you look at the chiplet deployment of this concept, you're looking at latency and performance. Power is a key element. You need a quicker wake up time as the CPUs go into a switch ping pong between an idle state and active state. So the connectivity needs to be very responsive of this behavior. Coherency is very key over here, so that you get a unified DMA access, unified CPU access for workload distribution from a kernel and software point of view. And bandwidth is less of a criteria. You're not sending terabits of data. So the beachfront is not so key. I'm not ignoring that fact, but it is not the essential aspect of it. You are trading off that with an importance given to latency and power, and that becomes the premises of the PHY, and that also becomes the premises of integration. Which class of quarks are you going to use? Are you going to use organic substrate? And all those parameters correct by construction comes into play, and that has a impact on the class of PHY or the PHY design what you're using for that application. And I've just given a reference that predominantly, I'm not saying hard-coded, that people prefer to use OpenHVI in this class of application. It's extremely well suited for this application for the various parameters I have listed or what we have listed. Again, there's no hard rule for such. People can use Bo also for it, but given the parameters and the application usage, OpenHBI comes out to be a winner in this case, at least from what we have seen on the surface. And again, the second example which we have highlighted, the workload specific SoC, it's more on heterogeneous class of things. So you have a core CPU, and then you have other peripherals, the IO peripherals like the Ethernet controller, the SATA, the USB, and the PCI sitting on the chiplet side of things. So you can have the entire core on a bleeding edge technology, 5 nanometer, 3 nanometer, and you keep stacking the core, and you have the DMA and the peripherals sitting on something like 7 nanometer or 6 nanometer or 4 nanometer. So there's a mix and match in the workload specific processing of the SoC. So both the cases are prevalent, and we can look into the next case for networking side of things as well. Ravi, is there a lag on my side, or because I don't see the next slide? Okay, thank you. So the next one is basically on the networking side. This is more on the fabric. Here, what's happening is as we go into 25 terabits of switching or 51 terabits of switching, a single monolithic die is kind of being challenged, and also the design by itself requires a large amount of MMU for the mapping and for processing of the routing of the port signals which are coming in. So folks are basically integrating the chiplet where they are using the layer 1 and layer 0 for the chiplet, and the main heavy lifting of the switch function or fabric function is done on the parent monolithic die. Here the key parameter is beachfront density. You are sending terabits of data from the parent die to the chiplet. So the link speed, latency, and beachfront density becomes very, very critical and important. What you're trading off over here is the power element of it. I'm not saying you can compromise power. That's not the claim. But instead of going into sub 1 picojoule per bit, people will look at 1.2 or 1.3. That's a little bit acceptable if you give them the beachfront density, because now the edge of the die becomes critical and you're sending terabits of data. So again, over here, Bo is a classic example which works well. And people prefer that because it meets that kind of a parameter of doing high bandwidth data transfer from one die to the other. There are other aspects from a chiplet PHY design point of view where you look at the bit error rate. You don't want to use the FEC because it adds to latency. Those are second order derivatives as we look into the integration and application usage of this kind of scalable switch fabric using chiplets. The next one, please, Ravi, the third example. The third one is basically now moving from the ODSA side to the IEEE side, where folks use the XSR 112 gig. And people use this for co-optics or for photonics integration. This is predominantly the optical engine, the OE. And over here, the criteria what folks are using is it has to be IEEE compliant. This is a CDR-based design as per the IEEE definition. There have been XSR in the industry which are not CDR or they are clock forwarded, but here we are basically looking at standardization stuff. So let's be clear about it. It's a pure traditional CDR based design. The insertion loss is basically under review by IEEE. There have been like 2 or 3 drafts with different insertion loss. So the XSR spec is not fully 100% like I would say blessed by the IEEE. There are different variants of it based on the insertion loss. And what you're trading off over here is power. Power is extremely high compared to our traditional chiplet-based PHY, what ODSA is looking at. And it's very obvious it's high because it's a CDR-based design. But again, for parity and for compliance point of view, it has to talk to a conventional MR or an LR or a VSR-based SerDes. And this is the example what people are using in pluggable optics or on basically midboard optics, where it basically talks to directly a switch SoC which has a 112 gig CDR implemented inside. The advantages: the switch doesn't use a long reach, it uses a VSR, it saves power, and design becomes much more simplified because now the thermal dissipation is kind of reduced instead of using an LR, and then you do an OE engine on the substrate by using an XSR. So these are the 3-4 different verticals. As you can see, the application requires different class of PHYs, and that was the point what me and Kevin were trying to bring up to this forum. And this again has implications when we look at the known good dies. Each of them will have a little bit of variance. The whole scope remains the same, but there will be a delta, a certain percentage of delta, which will be dependent upon these variants of the PHY because of the nature they have been designed for and the key elements associated with it. We have some few other examples, but this was a key message which we wanted to give. Kevin, if you want to add in something which I have missed, please chime in.
Yeah, I just wanted to say that I think the whole thought of having a panel on this is to identify the use cases and then have the panel address the question is, does this particular interface meet these requirements, or why this particular interface is good for this particular use case? Because I think for many, the idea of chiplets is people, as Rishi started with, is everyone throws it in the bucket and just think that the die-to-die interface is all the same essentially, and we're saying they're not. It really depends on the use case. So I think we're open to thoughts or comments from the rest of the team here.
So, for example, you'd get somebody from the optical world or an application that goes into these to see if it's got to be serial interfaces or will any kind of parallel data structure work for CPOs? Would that be sort of
Yeah,
one
I think that would be
panelist?
the interesting discussion, right?
Yeah,
We're
it
making
would.
these assumptions now, but maybe there's something we don't understand. And yes, for the optics, we're thinking serial, but maybe there's a reason parallel might work and we don't know.
Right. Yeah. No, that's of interest to me. Hence the question.
Yeah.
Well, if you think about that, if you go parallel, you only end up, if you look at what Ayar Labs has done with Intel's AIB, you only end up having to push the serialization stuff into the I can't remember what the name of the buffer is inside the optics converter, the transimpedance amplifier or whatever it is. So you don't take away that piece of logic. It's just where you break the line. So you still need to do the parallel to serial. It's just if you did it inside the processing package and had the PHYs there, to my point, I was saying, we need something like XSR with a specific protocol that I'm proposing OMI that we use everywhere. So when you talk to an HBM, you could talk to it with that interface. When you talk to an optical device, you would talk to it with that. And then the chiplets, the I/O chiplets, can become more simplistic. Either retimers or redrivers if you need them, or you actually package things so they're really tightly coupled to the. You need a modular pluggable chiplet approach as well. And XSR gives you enough reach. Maybe slightly less in XSR actually, based on what we've shown, gives you the ability to actually have pluggable chiplets rather than always having to be on the same substrate.
Sorry to interrupt, Alan, but here is my suggestion again. I don't want us to get into the solution mode. So this is the panel which Rishi and Kevin are proposing. So I have a question for Kevin and Rishi. Like, who should be your panelist? Like, do you have any idea? At least minimum 3. I think Bapi said in the past we need some sort of a general consensus from those panelists so that we can go forward with the panel submission.
I think so. Ideally, somebody from this particular space, like somebody from the CPU space or somebody from the networking space, would be the best ideal panelist, because if we have 4 verticals and we have representatives from these verticals, it would be better, I would say, because they are coming from that space, from that organization.
So
Rishi,
can we actually start by listing set of companies? We can converge on the names later, but maybe we can capture in some document. Maybe I'll capture it in the notes or something. Just set of companies which we can go to.
We can use the meeting.
Yeah, that's what I'm pulling. Can you put it in the chat so I can quickly open it? Yeah, thanks. And let me capture it as people are talking.
Explain a little bit what this panel is looking for. Is basically the question of between retime or not retime, or in general co-package optics?
So Shahab, this is not only a co-package optics panel. This is around interfaces and open interfaces and their applications and use cases. This slide just is talking about XSR interface, but it's not a co-package optics panel.
Okay.
Rishi and Kevin, correct me if I'm wrong, but intent is talk about the open interfaces and their use cases and application, and XSR is one of them.
Yeah.
Correct.
So, immediately I would say, based on this topic, we should absolutely get somebody from OpenHVI. That's, I think, a given. And I think that Kevin can help us, right? OpenHVI and Bo, our representatives, should be there. And then beyond that, we need some information about use cases. So some end users should be there. And that could be, Microsoft, Google, Facebook. And then we can have some of the networking folks also as a use case, right? So that could be companies like Broadcom, Marvell, I don't know others. So I'm just capturing few names and few ideas very quickly.
But how about the company like Cadence, Synopsys?
Yes. So I think for sure, because the implementation part will be done by EDA companies. So I think we should have Cadence, Synopsys.
On top of that, I think Cadence and Synopsys is good if someone can come and represent the XSR, because those two are, at least they are talking, they have the IP of the XSR.
I can present on the XSR if that's needed.
Yeah.
Okay, perfect. So I think we have OpenHBI, Bo, XSR, and XSR would be Cadence. So I think we have some structure forming. Okay. So far we have OpenHBI, Bo, XSR, Cadence, end users, Microsoft, Google, Facebook, Alibaba, one of them or two of them, no more than that. And then networking would be Broadcom, Marvell. Any other ideas?
Anyone from the optical side?
Like
I can ask someone from IR Labs if you want, but I don't know if that helps.
So XSR has a primary use case on the optical side. That's my understanding? Correct me if I'm wrong, but is that one area where we can bring optics discussion as well in context of XSR?
On XSR, DJ, my understanding is it's both for optical as well as even it's just serial interface.
Yeah,
right.
It's a serial interface, but under the optical standard.
Correct.
It's
exactly
under
exactly.
OIS.
Correct. It's been predominantly driven by the optical engine for photonics integration. And,
there you go.
Yeah. So because when you do the TOSAs and ROSAs, it's needed. Yeah, we can cover that in our presentation.
Exactly. So XSR will cover both the so Cadence can cover the optics side of it as well. And Rishi, if you have someone from optics you can bring in within your presentation or panel, more power to it.
Actually, I can talk to Dr. Ken Chen. He's our corporate VP and he is more into this optics side. I will see if I can get him into the presentation. Give me some time, 1 or 2 days. I'll confirm with him.
No worries.
So I think we can finalize on some of these panelists as a function of time. So Kevin and Rishi, one of you can now put together this abstract and submit.
Sure, we can do that.
Okay, because the deadline is next week on Friday, I believe. So like sometime middle of next week, and then I'll work with you guys offline in terms of how do we plan in terms of more logistics of this panel.
Just on the XSR there, obviously the optical perspective on XSR is as fast as possible. So I think that slide showed 112 gig, but obviously that is a huge impact on latency, so wouldn't be applicable for others. So you might want to stick with an NRZ approach, going up to 56 gig on the XSR, or however high you think you can go. So if it was going to be used more prolifically, that's the.
Ellen, I have a question. So you did open memory. I forgot the acronym for that one.
Memory interface, yeah.
So I think that's an open interface. I think you should be also one of the interface point of view here. That's my opinion. What do you think?
Yeah, no, I'd be happy to if you like. I'm trying to sort of be an average of everybody. You've got everybody got all these different interfaces, and I'm trying to say, can we not keep it to one? So yeah, I guess, and that's where I'm coming in.
Ravi, I guess a quick question I have is, what kind of logistical time frame? Because we have a lot of ideas right now, and if I count all the people that we want on the panel, we're at over 8 already, which logistically
So the way I see is OpenHBI 1, Bo another one, 2, XSR 3, end user I am thinking 1 or 2, so 3, 2, 5, and networking. Oh, okay. So I think I see your point.
Yeah. So I'm just saying is what kind of time frame are we talking about for a panel?
1 hour or best case 1.5 hour, but I think mostly it is 1 hour.
Okay.
And so the 1 hour, the structure I have seen maybe 5 to 7 minute talk from each one of them, and then moderator will open up for some pre-curated question as well as for question from the audience. So so you want to keep at least 20-25 minutes for questions, and then the rest is everyone will be talking about, as I said, 5 to 7 minutes of their take on this whole thing.
Exactly. I think the discussion is going to be critical for this because
Yep.
like Anna asked about, as Anu asked about, can I use parallel for this, or is it only serial for opticals? And what Alan brought up is, NRZ versus PAM4 because of latency. And I think those are discussions that aren't necessarily clear with people. And I think those are the discussions that are going to bring it up in the use cases, say, well, no, we can actually do it this way or this way.
Okay, so I think let's just keep what we have it here, and Kevin, if you and Rishi can submit this abstract next week, and then I'll work with you offline to get into the logistic and how do we do the panel moderation and all of that.
Actually, Ravi, just one. I mean, the general question here is argue where you've got different people's perspectives, but you're introducing a multitude of buses with good reason for each one of them. But then you look at it from the lens of, I mean, I can't speak for Microsoft, Google, Facebook, and Alibaba, but when you look at it, certainly if you're a processor company, you're going to say, well, what mix do I put on my device? How much of each for my customers? And so I think a key topic, almost a title of its own, is should we have just one, or should we have the best of each? The HBM, the bunch of wires, the XSR, and I think that's a core. We seem to avoid it. Everybody just keeps battling their own, and we don't have the conversation. And I think the audience, and arguably maybe the end users and the customers should actually have a vote. Now, I would also argue the end users like that you've got there are tier ones. And if we're really going to have an industry standard, you need tier 2s and tier 3s to actually be broadcasting in their view of a startup, a silicon startup, the VCs with $100 million or whatever. They've got to cut their beautiful processor and they've got to make a decision of how many of each of these interfaces to put on it. Anyway, so I think should we have one or should we have a multitude is one of the fundamental questions of this panel.
So I think at least, Ravi, we have some basic data point on the panel structure for Rishi and Kevin to submit, including list of companies which might be there. Is there anything else we need to close on for the OCP Global Summit next week?
I think in the last 5 minutes, I just want to ask with Anu, Mudasir, and Javi, are you guys on track to do your abstract next week?
Yeah, we are. So what we've done is between the three of us, we have finalized the abstract, and we are now going through individual company approvals for those of us who need individual internal approvals, and then we will be submitting the abstract before the deadline.
Sounds great. Thanks, Mudasir.
And also, Ravi, we've also scheduled a time with Roberto later today, so we make sure that we are in sync with what he's writing in his abstract, and there's clarity between the two abstracts as well.
Yeah. Okay. All right. I think with that, and Mudasir, I'm last time when Anu was sharing, maybe end of the month you will share at least how you guys are thinking and how you are progressing in your cost model. Are we still on track for that?
Yes, we are working on the tool, and the next time when you give us a slot, we can walk people through it. But keep in mind, it is complex and it has lots of things in it. So it'll definitely trigger a lot of conversation, and most likely in advance of that presentation, we'll probably share the document with a larger group so people can review it and come in and ask questions.
No, that's the intent, Mudasir. I'm sure it will create. So I'm thinking of 30th July. We'll spend either the whole meeting or half of the meeting on that cost model. If that sounds okay. 2 weeks from now.
Javi, Anu, is that okay for you?
Yeah, that's okay. But I'm thinking, Ravi, we need definitely the whole meeting.
Okay. So you have the whole meeting,
because I'm not sure how much we'll get through with the amount of debate we have with the teams, with the people in these groups.
again, we have to start somewhere.
Yeah. Sounds good. 30th.
All right.
Yep.
Sounds
We're
good,
on.
guys. So we are almost top of the hour. Any open before we close the meeting? All right. Thanks everyone for attending today's meeting. We'll reconvene in 2 weeks. Thank you so much.
Thanks, Ravi.
Thank you.